Some stuff we expected.
Super fun. All right, I'm gonna figure out these lights maybe. Can everybody see okay? Is this fine? Is this good? Okay. All right, so let's get started. The title of my defense is Rapidly Rotating Low Mass Stars in the K2 Photometric Monitoring Survey, which is a mouthful, but we're gonna be experts on what that means by the end of the introduction. But before I have a bunch of acknowledgments. I'm really excited that my mom and dad could be here today. They have supported me a lot for the last 29 years and 358 days. My birthday is next Thursday. So I'm really glad they could be here. My older brother's here. My oldest brother is not here because he has a almost 7-day-old baby, but they should be watching the live stream, him and his wife. And then my best friend for my whole life is here too. So thank you all, my family. I have a bunch of other acknowledgments. My committee, the chair of my committee is Dr. Lapine. The GSU astronomers are Dr. Martins and Dr. White. The physicist is Dr. Connors. And then my outside reader is Dr. Turntrump from the Ohio State University. We've had a bunch of collaborators. For the first paper that came out a year ago, we worked with Eric Pettigura and Ian Crossfield. They were co-authors on that paper. The second paper that we are working on now and totally going to submit before I graduate, we've been collaborating with Wei Chun. Maybe he's here. Hi, Wei Chun. For that paper, too, Leo and I tried to get some data that totally didn't work out, but I learned a lot about how to get radial velocities working with Leo. I saw you come in. Yeah, thanks, Leo. And then over the summer, I had an REU student, Kendra. She's an undergraduate at Augusta State. So we've had grants from NASA and NSF to fund my work. We have also gotten publicly available data from NASA, ESA, and Andrew Vanderberg, who is at CFA. I have a lot more people, okay? It takes a village. I want to thank everybody on Team Sassy Bassy. That's Bakyang and Netta and Ilya and Zach. Zach is probably not watching the live stream because he is, oh my God, Zach, yay! he is at the Lowell Observatory now, finishing up his PhD. Georgia State is really unique because the grad students all get along really well, and I'm really lucky that all of my roommates have also been grad students. I live with Bakyang now, and I did live with Caroline and Katie. I have driven across the country twice and back, once on purpose with Crystal, and once with Emily. And we've also traveled to conferences together. Me and Caroline drove to Texas one time, intentionally that time. As many of you know, I have been competing nationally and internationally in powerlifting kind of on the side this whole time. And my coaches are Eric and Kelsey Kenry. They live in Florida, and I couldn't have balanced all of that without them. And then finally, I want to thank Peter for literally keeping me alive for the last few weeks, and he also brought all the snacks. It is not beer, it's cold brew. Okay, so all my feelings are out of the way. We're just going to talk about science now. You're going to see this outline throughout the talk, so I'm not going to belabor it. We're just going to start with the motivation and background so that you understand what the title of my thesis is. So why do we care about stellar rotation? So stellar rotation decreases as stars get older. This was first noticed in the 70s with this paper by Alan Skumanich. What was his name? Andy, okay. Okay, so this plot here is plotting age on the x-axis, so older is that way. And the lines are 3 different lines, but we're just going to look at the red line in the middle, and it's plotting rotational velocity. And there's 3 data points on this plot. The Pleiades, the Hyades in the middle, and the sun at the bottom right. The Pleiades are 100 million years old, the Hyades are 600 million years old, and the sun is 5 billion years old. So this is a log-log diagram, so it's a nice straight line through all 3 of these data points with a slope of -1/2. And the reason that stars slow down as they get older is because they're losing angular momentum due to their stellar winds. So stars have these great big magnetic fields that are carrying away particles as they rotate, and that's going to cause the star to lose mass, and it'll slow down as it gets older. And this was formalized into an empirical relation called gyrochronology in 2007 by Sidney Barnes, because he noticed that stars, when they're very young, are all rotating with random initial velocities, but they will eventually all slow down onto one sequence. So the fastest rotating stars will slow down faster to this, I call it the zero-age rotation sequence, and then the slower stars, they'll slow down slower. So you can see that in this diagram. On the bottom are the Pleiades, and the Pleiades are still pretty young. A lot of the stars are still contracting onto the main sequence. So a lot of the stars haven't converged onto this zero-age rotation. But if we look at the Hyades, which are 600 million years old, all of the stars have slowed down onto this single line. And now as the Hyades get older, they're all going to slow down at a predictable rate. That's dependent on their mass. So if we look at these two data points, the Sun and 61 Sig, you can be convinced that they both lie on that line. And the reason that gyrochronology is really useful is because it's a way to age date field stars. So they don't live in a cluster. It's hard to get an isochrone age for a single star. So gyrochronology is a lot better for that. However, gyrochronology hasn't been calibrated for M-type stars. It hasn't been calibrated beyond B minus V magnitude. So that's what the x-axis is on these two diagrams. It's a B minus V color. It's a proxy for mass. Redder, they're less massive stars. And the Sun is a G-type star living right here. A lot of the reason that gyrochronology hasn't been calibrated for M-type stars is because we're missing M-type stars. We're missing M-type stars from the clusters that we use to calibrate gyrochronology. And we're going to get more into that later. And it's also been hypothesized, and we talked about this a little bit yesterday in Don's seminar, that gyrochronology might not even be appropriate, maybe at all. But it might not be appropriate for M dwarfs, which they're fully convective at M-type 3.5. So we don't know what is going to happen in this part of the graph over here. So 5.5 years ago, I came into Sebastian's office and I said, I want to fill in this part of the graph. And we went down a merry old path that you'll see. So what we originally wanted to do a long, long time ago was look for fast rotators because they're going to be the youngest stars. And I specifically wanted to look for M dwarfs because I wanted to fill in this part of the graph. And so we decided to look for stars rotating at faster than 4 days, because presumably they would lie somewhere in this part of the graph. They might be 150 million years old. So where are we going to get a whole bunch of stars? We're going to get our data from the Kepler telescope. So the original Kepler mission looked at one patch of the sky in the constellation Cygnus, and it stared at it from 2009 to 2013. And this is the telescope there on the right. And its main purpose was to look for planets, looking for transits in the light curve of the star. And the reason that the mission was so successful is because the telescope could point so very carefully without blinking, without moving, so that you could see those transits, you know, presumably if it's an Earth-sized planet around a sun-like star, once a year. So you need 4 years to get 4 data points. However, in 2013, when I first started at Georgia State, Kepler-2 was, the Kepler telescope broke. So there's 4 reaction wheels on board the telescope that are keeping it pointed so very carefully. But 2 of the reaction wheels failed in 2013, and so it was repurposed as the K2 mission. And so the way that the telescope was pointing, it was being balanced on one side by solar radiation pressure. So it's looking along the ecliptic plane, kind of rolling on its side, being pushed against the solar panels by solar radiation, and on the other side, 2 of the reaction wheels are keeping it pointed. So it's pointing at the ecliptic plane, and the field of view changes every 90 days. And earlier this week, it was decommissioned because it ran out of fuel. And I don't need it anymore. And so Crystal sent me this cartoon at like 5 a.m., and I had to add it to my slide. So the field of view changes every 90 days, which is great if you want to look at a whole bunch of stars, maybe not so great if the thing you want to observe happens on a scale longer than 90 days, but we were looking for stars rotating at 4 days, so it was fine by me. So we want to look at nearby M dwarfs, and so we're going to do that by looking at high proper motion stars. So you can see proper motion is what we call the apparent motion of a star across the background stars, and you can see that in this picture here. This is the same star, but its picture's taken across 4 years, and they're stacked on top of each other. So you can see how it's moving up in this picture. And the reason that a star will do that is either it's very nearby, and so its motion just appears very large to us, or it could be pretty far away and it's moving pretty fast. But those stars are a little more rare. So if we specifically choose high proper motion stars, we're going to bias our sample towards nearby stars, which is convenient when you're looking for M dwarfs because they're intrinsically faint. So where am I possibly going to find a large catalog of high proper motion stars at Georgia State? It's with the SuperBlink catalog. So this is the catalog Sebastian's been working on, I mean, forever. I don't know how long. Since '05? Before that? A long time. And '01? Okay. So SuperBlink is an all-sky catalog, complete with stars with proper motions greater than 40 milliarcseconds, magnitudes greater or brighter than 20th magnitude, and it's full of GKM stars. There are 2.5 million targets across the sky. Yeah, maybe more since Gaia. There's more now. We're going to say 2.5 million. I think this picture is kind of old. In the south, it's a little more complete now. Yeah. What we did was we cross-matched the SuperBlink proper motion catalog with the K2 field, and we found 58,484 matches. So those are my stars. And I plotted them here on the right. So we looked at the first 15 campaigns of Kepler. It starts at 0 and then skips 9 because that was a gravitational lensing mission. I couldn't remember what 9 did. So we weren't able to get any of the stars in campaign 9. So this is just right ascension and declination. I'm going to use this same color scheme for the whole talk. So black points and pretty much anything plotted in black is going to be all of the SBK2 stars, the 58,000. And then the red dots are the fast rotators, and I'm going to tell you how I found them. And so those are all going to be plotted in red throughout this whole talk. Okay, so now I know my stars, I have my sample, but we need to look at the data so that we can get their rotation. And the way that you get rotation from a star is from the spots on their surfaces. So stars, as they're rotating, they're going to generate a magnetic field. That magnetic field is going to poke in and out of the photosphere. It's going to leave these footprints. And that's what the spots are. And so a very young star will have a lot of spots on its surface. And as the star rotates, the spots are going to look like they're coming in and out of our field of view. When the spot is facing us, the whole brightness level of the star is going to be darker. Then as it rotates around, the whole brightness of the star is going to be higher. So if you just stare at the star's brightness level, it'll go up and down over time. And when the star is really young and it's rotating really rapidly, it has a lot of spots, the modulation is actually going to be pretty high and it's going to change really fast. So it's really easy to pick up with the K2 mission. As stars get older and they have fewer spots, it gets harder and harder to pick up that modulation. And in fact, K2 wouldn't be able to see the rotation of the sun, which would look something like that, pretty low amplitude. So the raw data from the K2 telescope is pretty messy. This is what it looks like. The black lines are the raw data, and then the red is the corrected. So neither of these are rotating. This is just an example of how messy it is. So I used Andrew Vanderberg's data reduction. He was, I think, still a grad student when he got his hands on the engineering data, and he worked on a pipeline, and he, bless him, put all of his data online. And so you can just download it with wget, which is great. So what his data reduction procedure does is it corrects for the drift. So the spacecraft is drifting along, and then every 6 hours the thrusters fire and it points back to the center of the field of view, and then it drifts and the thrusters fire. This is why it has run out of fuel now, is because the thrusters are firing all the time. And what that does is as the star is drifting across the camera, there's going to be changes in the sensitivity because it's a quantum, it's an electrical chip. So there's going to be different sensitivity levels across the chip. And so that's why as the star is drifting, you actually see a change in the brightness level. That's not real. So his data reduction procedure has to basically flatten that back out so that, in this case, this star isn't rotating. So when he flattens it back out, there's nothing in this light curve. In the earlier missions, about halfway through each of the campaigns, the telescope would point back to Earth, download all the data, and then flip back and look back at the field of view. So in the earlier campaigns, they all have this gap. So that you'll see that in a lot of my light curves. Okay, so this is, the top one is Andrew Vanderberg's light curve, and then I do a couple little changes to it for my data reduction. So time is on the x-axis, it's baryocentric Julian date, and then brightness is up on here. His light curves are all normalized to 1. So what we do is we want to normalize everything to 0. So for every point in my light curve, I'm going to take the original point, subtract off the average of the entire light curve, and then also divide by that number. So that's going to give me a mean normalized light curve where everything is just normalized to 0. So even though all of these stars have different intrinsic flux values, they're all going to just now be percentages. And so this star has like a 3.5% level amplitude, and I can compare it to other stars now, and I don't need to know the real flux. We also rejected really extreme outliers. I rejected anything with a greater than a 30% deviation. I didn't want to get rid of eclipses, but I just wanted to get rid of anything that I thought might not be real. So it was a really high threshold. Okay. I think this is one of my last equations. Don't be afraid. So the way we get the rotation period is using the autocorrelation function, and that is represented by this equation, and this is what it looks like plotted. So what the autocorrelation function is just looking for self-similarity in the light curve itself. So for every single point, Fi, we're going to look at that point and then compare it to Fi plus k, where k is a lag, and we're going to test a bunch of different lags, which is the rotation. So it's a really, really slow procedure because you've got to take this point, compare it to Fi plus k, all the way down the light curve, and then you move to the next point, compare it to all the points down the light curve, and you add all those up, and you divide by this normalization factor. And you do that for one lag value, and then you test another lag value. And we tested lag values from 0 to 35 days, half the length of the light curve. And this is going to produce a kind of sinusoidal looking plot like this, where that first peak is the rotation period, because this is where the light curve is correlated with itself. That means you pick the right rotation period. And then every peak after it is an alias. So it's just multiple. For this guy, the rotation was like 1.5 days. So the next one is 3 days, and so on. If I were really good at writing Python, it would have been really easy to say, hey, tell me where that first peak is. And we spent like 8 months trying to do that. It was really annoying. And Sebastian said, this is like a really well repeating frequency. Why don't you just take the FFT of it? And that can give us a good first guess. And I said, you're crazy. And I didn't, and then I finally did. I was like, this is weird. Why would I do that? So the fast Fourier transform is basically it's just taking different sine waves and fitting it to this data. And eventually it's going to find the right sine wave, and it's going to produce a really big spike in this power spectrum. And so I take this big spike, and I go back, and I fit the first 5 peaks to give me the actual rotation period. And then we wind up not needing to confirm by eye, because I was finding when I was asking Python, just give me that first local maximum, it did not like it. And so if I found this repeating frequency, then I could use that to get the rotation period. And we wound up with 1,113 GKM stars with rotation rates faster than 4 days. So these are my babies that I've been working with for years now. So you'll humor me if I show you a few light curves. I'm not going to go like super into them. I just want you to like understand that this took a long time. Everything I've said up until now, it's been only like 20 minutes. It took me 3 years. So you can see the gaps in the light curves. Different, I think there's like a little flare on this one. I think I picked some more. Yeah, this one like that maybe is a little planet hiding in there. That was the original mission. The collaborators we were working with, they were looking for exoplanets. Just a few more light curves. What's really interesting is you can see, even though the... Yeah. One thing that's really cool is the pattern. So these spots are moving around and migrating, coming in and out because the magnetic field itself is changing. So the pattern that we're going to see changes. Like you can see in the upper right, the actual pattern of the light curve itself is changing because those spots are moving, but the frequency, the rate at which it's changing is still the same. I mean, the star is still the star. It's just that the spots look different now. Okay, up into this bullet point, 3 years of my life. And, and the original, I want to remind you why I was doing this. We were looking for nearby young stars because I wanted to fill in that blank part on the gyrochronology graph. Spoiler alert, I didn't do that, but that was what we were trying to do. And so because we were looking for these stars that we could use to calibrate gyrochronology, we wanted to independently verify that these stars were young, because then they could be used to calibrate this young end of the gyrochronology calibration. So the first thing that we did, this was before Gaia, we made an RPM diagram. So for the astronomers in the room, you can read an RPM diagram kind of like a color magnitude diagram. We have G minus J magnitude on the x-axis, so redder stars are that way, less massive. And then what we are plotting is Hg, that is the reduced proper motion. And so this is the equation for that. It's G plus 5 log mu plus 5, where mu is the total proper motion. And this equation can be rewritten so that it's m plus 5 log transverse velocity minus 3.38. So this is kind of like a velocity diagram. So stars that are moving slower through the disk of the galaxy are higher on this diagram, and stars that are moving fast through the disk are lower on this diagram. And so stars are born in the disk of the galaxy. As they move around and orbit the center of the Milky Way, they're going to have tidal interactions, and they'll be puffed up into the thick disk, and they would then move lower on this diagram. So young stars should be pretty high on this diagram. So most of them are. Don't ask me about the box. We'll get to the box. So that was reassuring that, you know, these fast rotators that we found seem to be moving slowly, and so they were probably young. And then Gaia, praise be, came out. So now we have their real distances, and we were able to make an absolute magnitude diagram. So again, G minus J on the x-axis, and now we're plotting mg, not hg. So this is the real brightness level. And so young stars are still contracting onto the main sequence. They're puffed up because they haven't fully formed onto the main sequence yet, and because they're bigger than they would be of a main sequence star of the same mass, they're more luminous because they're just physically bigger and putting out more light. And so they'll be brighter, which means they'll be higher on this diagram. And so again, this whole time, black points are all SBK2 stars, and the red points are the fast rotators just overplotted. So it does seem that my red points are higher on this diagram. Okay. Then the last, we're trying to convince ourselves that these stars are young. We looked at a color-color diagram. So the x-axis is G minus J, redder stars are that way, and the y-axis is the Galax near UV magnitude minus the Gaia G magnitude. So redder stars are up. So what we expect stars to do is that as they're getting redder, they're going to be fainter in near UV. And so they'll follow along a line, just a linear relation. As they're getting redder, they're getting redder. But if a star is really young and magnetically active and it has a lot of excess UV magnitude or UV flux, it's not going to follow along on this line. It's actually going to be lower down on here. So an astronomer can look at this graph and say, oh yes, all these stars are young, because these stars in this area over here have a lot of excess UV flux. And these are probably all white dwarfs. You'll have to consult my thesis, but I think there's something like twice as many red points in that area as there are following along the regular trend. So making all these plots, trying to figure out if my stars were young, we had 3 different side projects. And I'm going to tell you about all of them. The first one is identification of some candidate nearby young moving groups. What is a nearby young moving group, you say? So nearby for us is 150 parsecs, which is like 500 light years. And so stars are formed in clouds of gas together, and they're going to be loosely gravitationally bound to each other. And they're going to physically move through the galaxy together. And they'll be tidally disrupted over time, and they'll eventually disperse, and that's what we call a field star when they're no longer associated with a group. And that process takes about 500 million years. So we expect any of these groups of stars that we see moving together through the galaxy, that they're all young. And then we're specifically looking at nearby clusters so that we can find those missing M dwarfs because they're faint, which is explained on this slide. So these known nearby young moving groups, this was your former student, Josh Schlieder, came up with this kind of idea that we might be missing these M dwarfs because they're intrinsically faint. So what we usually do is if we identify a star that we think is in a nearby young moving group, we then go, okay, so it's moving together through the galaxy with that group of stars, but is it also bright in UV or X-ray, these other indicators that the star is young? And if it's not, then we say, oh, must not be a young star, it's not in that group. But the limiting magnitude of Galax is 22 in the near UV. So we might just be missing these stars anyway, because M dwarfs are faint. So that was this whole idea that maybe we have overlooked them, and they really are young. And our hypothesis was that we could just use rotation to be the independent verifier instead of UV. So this is a kinematics plot. We're plotting on the x-axis is the galactic longitude, and the y-axis is galactic latitude. And those are all the 15 campaigns. The black points are superblink, and the red points are the fast rotators. So we expect these young stars to be living in the disk of the galaxy. So they're going to have low velocities. And the range on these boxes is all minus 80 to 80 kilometers per second. And we expect them to be slowly moving through the galaxy. And we also expect them to be maybe associated with the known moving groups that we already know about. We want to say, are they a part of these groups? And that's what these black boxes are on here. They're kind of an average velocity of the nearby young moving groups. And we were just seeing, are our stars falling in this box? The different color boxes are the clusters that Kepler targeted on purpose. Yes, so the Hyades and Pleiades were in campaign 4, Beehive or Persepion 5, the Hyades again in 13, and then Upper and Lower SCO were in campaign 15. It's not a cluster, it's a star-forming region. So what we did, we just by eye looked for clumps in these diagrams, and we thought, you know, maybe these look like they're moving together through the galaxy. Maybe it's a group of stars. So we identified clumps in campaign 0, 1, 5, 11, 12, and 14. So I drew these little boxes on these diagrams, and they might look like they're moving through the galaxy together, but they might not physically be next to each other, because you can imagine two stars just happen to be moving in the same direction, but they might be really far apart. And so all of the boxes that were in those little squares, I then plotted their distances to see if they were physically next to each other in space. And so the red points are all of the fast rotators, and then I've overplotted those different boxes in the same corresponding colors. So yeah, the Hyades and the Pleiades and Upper and Lower SCO, they're all really bunched up next to each other, so that's good. We're recovering those groups. Campaign 0 and 1, they look pretty spread out, so I'm not really convinced anymore that those are really near each other. They just might have been, maybe my eye just thought I saw a clump when I didn't. But campaign 11 and 12 and 5, and the blue box in campaign 14, you know, you can be convinced that those are all physically close to each other as well. So we recovered 232 candidate members of the Hyades, the Pleiades, the Beehive, and Upper and Lower SCO. And then we identified 66 new candidate members of these cleverly named Campaign 5 group and Campaign 14 group, Campaign 11 and 12. The big takeaway from this diagram, so this is the same velocity in the L and B. I just put them all together. You can see that these are pretty loosely associated with each other. They're not a cluster of stars. They are dispersing. They eventually won't be a cluster anymore. The Hyades and Pleiades are open clusters. They're not really good. Maybe some of the outer members will evaporate, but they're going to stay compact forever. So the question is I didn't really fill in the blank part on the gyrochronology plot, but we at least want to maybe investigate if the stars that we found are following some sort of mass-age rotation relationship. So first we'll look at the clusters that we know their ages. So Upper and Lower SCO are 50 million years old, and we've got G minus J magnitude on the x-axis, and then rotation is on the y-axis, so slower is up. And so on average, Upper and Lower SCO are higher on this diagram because they're still contracting onto the main sequence. So stars are formed in these clouds with some intrinsic initial rotation, and as they contract and become a star, they're going to conserve their angular momentum, and it's like if you're spinning in a chair and you bring your arms in, you're going to spin faster. So a pre-main sequence star is still rotating slow. I mean, these are still rotating really fast, like, let's be honest. But they're rotating slower than they will once they get on the main sequence. And then we look at the Pleiades, which are 100 million years old. They've fully converged onto the main sequence, most of them, and they are rotating faster on average than Upper and Lower SCO. And the Hyades and the Beehive are 600 million years old, and now they've started to break and lose angular momentum. They've started to slow down and move upward on this diagram. So if we look at my groups of stars, you can be convinced that the average rotation rates are pretty fast, similar to the Pleiades, which suggests that they're equally as young. And in astronomy, we're fine if we can say, like, yeah, it's less than 500 million years old. I'm fine with that. That's kind of as far as we went with that project. We'll stop there. The next side project, we did some other stuff. The next side project was looking for white light flares. So stars that have magnetic fields, the magnetic fields will poke up out of the photosphere, and they'll get twisted and they'll break. Is Jane here? No, okay, so I can, that's how it works, y'all, I'm the expert. The magnetic fields will break and they'll produce flares. So you can see that here in this picture of the sun from the SOHO satellite. This is a prominence, and then this is a flare, so that magnetic field has broken and produced a flare. They occur randomly, they occur frequently, and they're pretty complex if you look at a light curve of them. They increase very rapidly and then have a power law decay. And they can last anywhere from 30 minutes to several hours. Unfortunately, the Kepler cadence is 29 minutes. So we're either missing some of the very fast flares, or the longer flares are only going to show up as 1 point. Like, if we get lucky, it's like 2 points. But we wanted to look for these flares. This is what they look like in our light curves. They're just single points. So the flare finding algorithm that we wrote works like this. So the top panel is the original light curve, and we do an iterative boxcar smoothing. So we start with a box that's 20 hours wide, and you take all the points in this 20-hour wide box, you calculate the average, you reject the outliers, and then you move to the next 20 hours slice. And you do that all the way down the light curve. And so now you have your new light curve you're going to work with. Now you take a box that's smaller, and you work all the way down. You're rejecting 3 sigma outliers every time. And our final box is 4 hours wide. And so we're left with a nice, beautiful, smooth light curve, which is the center panel. And if you subtract the middle panel from the top, you'll get this nice flat light curve, and all the outliers are just flares. So we were looking for those little points, those red ones. So I had 2 samples of stars. I had my 1100 fast rotators, but I also, as a control group, looked at 908 slower / non-rotating stars. Most of the astrophysical signal has been removed from the K2 stars because Andrew Vanderberg, he wanted to find planets. He tried to preserve some of the rotation, but anything longer than maybe 10 days, he's removed. So I don't really have very many stars even rotating slower than my 4-day sample. So we found 730 of my 1100 fast rotators were flaring, and 628 of the 900 slow / non-rotating stars were also flaring. But it's not, you would think, like, well, why are the fast rotators flaring at basically the same amount? As many of the fast rotators are flaring as the slow rotators. But the faster rotators are flaring at a higher rate. So even though, and this diagram only goes out to 4 days, so we got rotation slower that way, and then this is the amplitude of the light curve itself in log of the percent. So higher amplitude is up. And then the open symbols, I did not find flares. The filled in symbols, I did find flares. And then the size of the point is how much it's flaring. So you see that the fastest rotators are flaring more and flaring at a higher rate. So slower rotators will still flare, but the fastest rotators are flaring more. We also did some other stuff that we're not going to talk about. So this is the final side project, and let's see. And you're not allowed to have favorites, but this is my favorite. So we're going to talk a little bit slower about this one. So we found some fast rotators in the halo. What is going on? The galactic halo, so this is a Sombrero galaxy, but we live in the same kind of galaxy. It's a spiral galaxy. And this kind of fuzz around the edge is the halo. So these are the remnants of when the galaxy first formed. They're old and metal poor. In our galaxy, halo stars are about 10 billion years old. They shouldn't be rotating. If they are rotating, it's hundreds of days. K2 can't pick that up. But we found 32 halo stars that were rotating. So this is that same RPM diagram from before, and this box that I drew on there is the halo. So stars that are in the galactic halo are moving very fast, and so when they're not always moving very fast. When they're furthest away from the center of the galaxy, they're moving really slow, and then they'll plummet down through the disk and around. So if in our proper motion survey, if we happen to be picking up a halo star, it's because it's in the disk flying through really quickly. So it's going to be very, very low on this diagram here because the velocity is so high. So there are 12,470 SBK2 stars in the halo, and there's so many because we were specifically looking for halo stars. And 32 of them were rapidly rotating. So the first thing we want to do is say, is this really happening? Like maybe K2 picked up a nearby star, like maybe there's some contamination. So in these pictures, the black one, that's all the K2 postage stamp. So the K2 camera is pretty big, but it would take a really long time to download that whole thing. So they just download little squares where they know the stars are. So that's called a postage stamp. And then on the right is the same of each of these stars, but it's the POS image. So we wanted to check, like, did we get the right star? And is there something else on the postage stamp that maybe none of these stars were actually rotating, we just happened to pick up a neighbor. We found so this is just 4 of them, but we found in total, I think 4 of the stars were contaminated. But in general, not in this case, but in general, our star was the brighter one. So we could still be convinced, okay, there's a contaminant, but maybe our star is the real signal. And then we looked at their actual light curves. So we had 12 confirmed rapid rotators. We didn't just look at those 32. I also looked at all 12,000 in case we missed something, which we did. We found 5 more by looking by eye. So yeah, we had 12 confirmed rapid rotators. You look at their light curves, it really looks like a bona fide rapid rotator with a giant velocity. So my code, many years ago, maybe when I was smarter, I would have found a way to not pick out eclipsing systems, but it was convenient that we wound up finding eclipsing systems. It can't tell the difference between the two. It just sees that repeating signal. And it wound up being really interesting, so we kept them in. We have 9 confirmed eclipsing binaries. The top panel is a portion of each of the K2 light curves, and then the bottom panel is folded. So once you find the orbital period, you can just kind of stack the light curve on top of itself so that you can just see the eclipses all on top of itself. We also found 4 confirmed interacting binaries. So these are binaries that are so close to each other, they're touching, and it's sort of like the star is always eclipsing itself. And so when you look at the light curve, the top panel on all of these, it looks sort of like a rapid rotator. But the amplitude is much larger. Most of the rapid rotators, the amplitude is around 3%. For the interacting binaries, it's more like 15 and 20%. And the orbital period is much faster. These are around like 4 hours, these 2 stars whipping around each other. And then the bottom panel is the phased light curve. So we looked at their postage stamps. In general, they weren't contaminated. We really looked at the light curves. There really was something going on. And in some cases, it was an eclipsing system. And then all praise Gaia. We have their real distances now, so we can get their velocities based off of their parallaxes. So this is the same sort of velocity diagram. It's galactic longitude on the x and latitude on the y. And we expect disk stars to have velocities around 100 kilometers per second. So anything greater than that, we would say it lives in the halo. And my subsample of these halo stars, that's what that circle is here, is the 100 kilometers per second division between the disk and the halo. And all of my stars lie outside that division. And one of them, so the different symbols are the eclipsing systems are the triangles, the fast rotators are the circles, the contact interacting binaries are the squares. And one of them, yeah, he has a really large velocity at 700 kilometers per second. So these rapid rotators, why are they still rotating rapidly? We know the modulation that we saw from the binaries is because we're seeing the eclipses, but why are the rotators still rotating so fast? They should have slowed down at 10 billion years old. So we think that these are interacting binary systems. They're not actually touching, so they're not like a contact binary, but we think they're still pretty close to each other so that they have exchanged angular momentum throughout their lives and have kept them spinning faster. Okay, yeah. So the eclipsing systems we think are these same sort of systems, but they're at an inclination angle so that we can see the eclipse. So in this case, the two stars are pretty close to each other, but they're not oriented so that we can see the eclipse. But we think that the eclipsing systems are the same sort of system because if we look at the light curves of about half of the eclipsing systems that we found, we can also see that they're rotating. So we think our fast rotators are fast rotators that are they're interacting binaries where we can't see the eclipse, and that the eclipsing systems are the same close binaries. We haven't been able to prove that. I'm going to talk about that in future work. Okay. So I've been working with Ellie for the last few weeks. She has been reconstructing my light curves into heat maps. I think it's really interesting what she's been working on, but I am obviously leaving, so give her your light curves. I guess I could just email all of hers and never email her all of mine and never ask her about it again, but this is really cool stuff she's been working on, so if you have light curves, get with her. The candidate nearby young moving groups that we found, we need to verify that they are real. And it would be really interesting if somebody could fill in that part of the graph that I never got to fill in because we went down these other rabbit holes instead. I know that a lot of the reason we didn't go down that rabbit hole is because someone at St. Andrews was also working on it, so we kind of had to go in a different direction. But I haven't seen him publishing anything lately, so it's still to be done to calibrate gyrochronology. So the flares analysis, we only looked at the fastest rotators. There's other studies that have been done, this is by Stelzer 2016, that has shown that the amplitude of the light curve decreases as the star is rotating slower. And in this work, he was also looking for flares. The green points are flaring and the red aren't. And he was looking at 124 SBK2 stars as well with, so the same sample of stars, but much fewer of them because he doesn't have access to the full catalog. So basically, I only looked at this part of his work, and he was able to go out to 10 days rotation, and so if somebody could like put those together, that'd be great, and use a different telescope, not K2, obviously it's dead now, but the cadence is really slow. Something like TESS or Mirth that has like a 1-minute cadence would be much better to pick out these really detailed flares. So combine these two and use a better telescope, or a more appropriate telescope. And then finally, if I were to stay in astronomy, this is what I would want to do. So somebody do this, please. We need to get spectra of the halo subset to confirm that they really are binaries by getting their radial velocities, and we can get masses from eclipsing systems, and that's really important for understanding stellar evolution, especially for these halo stars, which prior to this, there were only about, I think, 6 known eclipsing binaries in the halo. This is what Wei Chen has been working on. So particularly with this project, it's like someone wanted me to do a postdoc because there's eclipsing binaries all the way down the color range from, this is like late K down to late M. Okay, I'm at 11:45, so I'm just going to leave up my summary, and I will take any questions that you have. Hi. Mm-hmm. Oh, and it wasn't for all of them. The amplitude needs to be high enough that you can pick it out. You can just see in the top panel that this is the rotation modulation. It's pretty small because of the scale. If I could like take out the eclipses and plot it differently, you could see. That should probably be done for all of them.
Can you tell which of the two is rotating?
So I think with these guys, if it's an eclipsing system, the eclipsor, the smaller of the two dips, is not contributing a lot of light to the rotation because it's probably like an M with a smaller M or a K with an M. Hi, Zach. Zacky.
Hey.
Hi.
Oh, it's loud. Good talk. Run the final lot of the flares section.
Like the amplitudes?
Yeah.
Yeah.
There's a clump at lower amplitude at like 1 day.
Yeah, there is, isn't there? You know, I don't know. If I had to guess, okay, so they're really low amplitude. Yeah, I don't know. It might just be instrumental. It seems kind of weird. I don't know why something would have that amplitude and that rotation period in particular. Like maybe they're eclipsing, I don't know. I guess you could just look at them, and if it's like, oh wow, they all are the same thing, like, oh, then that's just where these stars live on this diagram. But if they all look different, I don't know, I guess you can be like, there's something in the light curves making it do this. Yeah. Somebody who has more time could go look at all of those light curves and see what they're doing. I haven't, like, I must confess, I've probably only, like, of the 58,000, I've only looked at a few hundred of them. Mm-hmm. Mm-hmm. Right. Yeah, yeah. And now that we have the Gaia distances, we would be able to do that because we can see how far away they really are, get their real luminosities. The other plot, the other work that I was showing, Stelzer, he did do that. And I can't remember what conclusions he found, but he was working on getting real luminosities with Gaia to see how the flares compare on M dwarfs to other types of stars. But that just wasn't, yeah, the direction we were going. But yeah, that would be really cool. Mm-hmm. 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 Yeah. Mm-hmm. Yep. I didn't do that. But it would be, yeah, it would be interesting. Mm-hmm. Mm-hmm. Yeah, we did. We worked on that for a long time. So I showed like probably my like most beautiful light curve, and it has a the autocorrelation function is all the peaks are the same level. So I guess that's telling me the spots are really long-lived. But we found some really cool patterns. Like some of the autocorrelation functions will decay and come back, and it's like this beat pattern. And we tried to divide them between steady and decay autocorrelation, and we looked for all different kinds of patterns. And I can't remember why we kind of stopped working on that. I presented it at Cool Stars, but I can't remember. Yeah. Mm-hmm. 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 Oh. It's like I should listen to you. Yeah, yeah. We should probably redo all the rotation periods using the smooth light curves. Yeah, like 10% maybe. Hmm? I want to go to Crystal first. Yeah, so we start with a 20-hour wide and take the average, take out the outliers. And those outliers we replace with the average. Yeah. Oh, yeah, so, I think, where are you? You're this way. So I wound up, I didn't say this, we only took anything with a pretty high residual. And like, yeah, maybe some of those, what I'm calling a flare, is just crap. But I have a line in there that it can't just have one point. Like I wanted to have several flares before I'm like, okay, maybe one of those isn't real, but yeah, I have a line in I have an if statement that only takes, I think, 4 flares before I'll throw it into my pile of flares. Yeah, like we want to see it more than once. Like if there's just one, like maybe we did only catch one flare, but maybe it's not anything. So yeah. Mm-hmm. Yeah, Super Blink's updated to Gaia DR2. Mm-hmm. About binaries? About binaries? Okay. Who knew? Mm-hmm. Mm-hmm. Mm. Mm-hmm. We did. I gave Zach my stars and asked him to see if he could find any nearby companions, and he couldn't find any companions. It was like a year ago. But that doesn't mean that they're not there. They could be really, really faint. Or they could be really close, yeah. So, yeah. Okay, yeah. Okay, yeah, that makes me feel better that he didn't find any companions. Yeah, we would, I guess, need to find out if they're binaries or if they're single stars. That was what Leo and I worked on. We tried to get radial velocities for one of them. It was, yeah, they were really low signal to noise.
They really are.
You'll be able to tell just from that.
Yeah, on the
Mm-hmm. Yeah, you'll see H alpha, yeah. Somebody please do something with my halo stars.
at least as a demonstration.
Yeah.
Lots of work, lots of detail.
Well, you know, that's a really good question, especially very personal, considering. I don't know. I hope that if someone asks me what I did, that I will at least remember the Halo project, because that is really fascinating to me. I'm really excited to get this paper out, and yeah, I hope I remember that at least 10 years from now. And all of you. What do you remember 5 years on, Gagny? He still remembers a lot, so he would like drew out for me. Yeah, yeah. I was like, I know where Secret 1 and 2 is. Yeah, he drew out his old master's thesis for me at work. Like Kramer made me redo everything, and it was still right. My slides, all of my figures were gone this morning. And I had to put them all back in. And my mom and dad are like setting this up, and I'm putting them back in. I'm like, this is why it took me so long. Like, it's just crap breaks for no reason. Any more questions? Wade?
Are there any more donuts?
Wasn't it just an illustrative example? Keep going. We're going. These? Oh, the next one? Well, this isn't, these are two different stars. Oh yeah, it's BJD, yeah. Minus 2. These are future light curves. Is that it? Did I do it? Goodbye, live stream. Thanks for watching.
Where are you guys? Sean Watson.